Log on, tune in, find out. Another good idea from Cambridge.
Of the non-orientable surface.
Okay, so first of all, I'd like to thank the organizer for a kind invitation that I can talk about my work here. This is a joint work with Melissa Liu. So we try to use the representation right to explain this whole thing, because this is the subject of the concentration this weekend. So let's start with some notation. So G is a compact, connected Lie group, and sigma, we denote it by sigma Li, which means that it's a compact closed surface. So if I is equals to 0, so your I can be 0, 1, and 2. So if the sigma is sigma L0, then it is a Riemann surface of genus L. We require it to be bigger or equals to 1 so that we don't consider the Riemann sphere. And if it's sigma L1, then it is the connected sum of a Riemann surface with a Klein bottle, with an RP2. And if it's sigma L2, then it is the connected sum with a Klein bottle. And so P is the principal G bundle over sigma, and so we know that it is classified by pi 1g if your sigma is orientable, and it's pi 1g quotient 2 pi 1g if sigma is non-orientable. So this makes sense because this is abelian, okay? And we can consider the space of connections on this principal bundle. So we know that this is an affine space, and the associated vector bundle is this one forms on sigma with values in a joint bundle. And the space of flat connections, so those connections which has zero curvatures, so there is obstructions for principal bundle to admit flat structures. So if your space is orientable, but for non-orientable, all the principal bundle admit flat structure. Okay. Now, this rest of the notation, this curly G is the gauge group, and G naught is the based gauge group. And so what we're interested is that this gauge group acts on the space of connections, And in particular, if the space of flat connection is not empty, then it acts upon it. And so this quotient space, is what we are interested in. And so we want to study this space when sigma is non-orientable. And what I mean by taking the Morse theory approach is that, so you want to look at this space and you want to look at the gauge equivariant Poincare series for the space of flat connections. And the way we study that will be using the Morse theory approach. So when sigma is orientable, that's the classical work of Atiyah and Bott. And so as I go through how we do this, I will also review their work. So first, sigma is orientable. So this is Atiyah Bott's work. So we equip sigma with a canonical metric in the sense that its curvature is constant, and we normalize it such that the area is equals to 1. And so our sigma now is a scalar. This is now scalar. And AP is also scalar. So we look at this AP as the one from sigma to the adjoint bundle. So the scalar structure is the following. You take the trace of A which beta and you integrate it over sigma. So alpha beta lies in the tangent space, and the complex structure comes from the Hodge star operators on the surface, and the compatible Riemannian metric is by taking the trace of A which star beta. So that's the scalar structures on this space. And so on this space, we can define this functional called a Yang-Mills functional. So this functional is defined by taking A goes to, so if FA is its curvature form, so it's a 2 form on sigma with values in a joint bundle, then this is by taking the L2 norm of that. So you have trace FA which star FA. So this is the Yang-Mills functional, and so the critical points of this Yang-Mills functional are called Yang-Mills connections. And so we denote this NP to be the space of Yang-Mills connections. So naturally, if the principal bundle admits flat structures, then so So if flat P is non-empty, then this lies inside of that. Flat are naturally Young-Mills connections. So they are naturally Young-Mills. And this basically gives you the stratification. So right now I would just write out something like this. And for now I would just say that they are connected component, but I will give you the details of this mu later. So this is, for now you just consider them as connected component. And you have the stable manifold. So that gives you the stratification. So this is roughly the idea of how this stratification comes from. And so a quick remark. So if P admits the flat structure, then the absolute minima of LP is 0, and they are achieved by the flat connections. So this is quite clear. But if P doesn't admit flat structure, then the absolute minima of LP is achieved by the central Young-Mills connection. So what do you mean by this central? So look at an example. If G is UN, and say the degree of P, or the first chain class of the principal bundle is 0, then it has flat structure, then the absolute minima of LP is just 0. Now if the principal bundle is of degree K, which is non-zero, then you don't have flat structures. But the absolute minima is achieved by those central, and they are just 4 pi square K squared divided by N. So the reason for that is, can I write it here? Okay. So you see those central Young-Mills connections, if they are like that, then this connections, the curvature of that has a particular form. So this is the area form such that the integral is 1, which we required. And this x is a constant, which looks like this. It's a diagonal matrix, and on the diagonal part, it's just K divided by N. So when you plug this into this Young-Mills functional, then what you get is just minus 2 pi I squared. So this is LPA. So when you plug it in, you get minus 2 pi I squared times N times Kn squared. So that's how you get your minima. And those are the central Young-Mills connections. So you would always have some kind of minima. Okay, so that's how you get roughly the certification on the space of connections for a Riemann surface. Now, if we want to do similar things for the non-orientable surface, So we want to define some kind of Yang-Mills functional. Then there's two ways around it. One is look at the orientation bundle, and the other way is look at the orientable double cover. So we will take the orientable double cover approach. Okay, so let sigma now be a non-orientable surface. So we also equip with a canonical metric such that the curvature is constant and the area of that is 1/2. Okay. Okay. So we look at the orientable double cover. Of sigma. Now, if sigma is sigma I is non-zero, then the double cover is a Riemann surface or just an orientable surface where the genus is 2L plus I minus 1. Yeah, and then so there is this tau, the deck transformation, from sigma tilde to sigma tilde, and we have a projection going from sigma tilde into sigma. So now you equipped sigma tilde with the pullback metric. And with all this orientation, and so tau, notice that tau is orientation reversing. So together with this metric, so the area is now 1 and is now Taylor with this metric and the orientation. Okay, good. So we can look at the bundle. Maybe I will write it. Okay, so consider P is a principal G bundle over sigma. So sigma is non-orientable. So we have this principal bundle, then what can we say? First of all, we can look at its pullback bundle over the double cover. So then, first of all, the pullback bundle over the double cover is always topologically trivial. So this you can check by looking at the obstruction class. So usually that's how you define or you know what the topological type of the bundle is. So this is, you can check and then you will realize that they are really trivial. And then secondly, so this, oh sorry, I should write it a little lower. So secondly, you have this relations. So P tilde over sigma tilde, tilde. So this is the tau. And you have pullback bundle. This is sigma. This is the projection. You have this P. So this is the pullback bundle. And so this induces a tau here. So we would write it as tau tilde. So this tau on sigma tilde covers tau on the base, and such that the p tilde quotient out by this tau is our p. So there's a way to see how you get this tau tilde. I will just say it here now. So because we know that they are topologically trivial, so we can fix a trivialization.
You mean the tau tilde from P tilde to the line below the diagram?
Oh, sorry. Yes. Thank you very much. Yes, thank you.
From sigma tilde.
Yes. Okay. So the way to look what this tau tilde is that, so we fix a trivialization on p tilde. So say this is sigma tilde times g. And so this, we can define tau tilde s. We have a subindex here. Goes from p tilde to p tilde by sending x h to tau x sx h. And where this s is a map going from the double cover into G, such that S tau x is equal to Sx inverse. Okay, so with this tau s, you can look at the quotient under this tau s. So p tilde quotient out by this tau s gives you a principal bundle downstairs. And this principal bundle, its topological type can be determined by this x, by this s. This. There is a very precise way to see it. And so you just choose the s such that this quotient bundle is the same you start with. Okay, so so p tilde tau s is a principal G bundle over sigma, and its topological type can be determined from S. And so basically you just choose S such that, so we just choose as this map so that this is equal to our original bundle that we start with. So that is exactly how we get all the principal bundles over the nonorientable surface. Because as you see in this first point, all the pullback is topologically trivial. So you don't see anything upstairs. So the way to recover all those structures is by taking different tau. Okay, so that will give you back all the different topological bundle downstairs. So this is the second point. And thirdly, so we have this tau tilde that will induces a tau tilde star on a space of connections upstairs. Okay, and so this tau tilde star is, so I forgot to say, I don't know if I erased it already, the deck transformation, right? So here, so this this tau with this Kähler structure, this tau is anti-holomorphic, anti-symplectic, isometric, involution with no fixed point. And so this is also Kähler. We know that this tau tilde star is also anti-holomorphic, anti-symplectic, isometric involution.
Excuse me, is the S unique? You say choose S so that the quotient is P. Is that S unique?
No, you have a lot of ways to do it, but you can say you fix. You can actually require this as to be a constant. That is also okay.
There are several choices for the lift.
Yes,
right?
yes. But you will get the same thing.
The same what?
You will get the same thing. After quotient, you will get the same thing. If they are...
But these are different lifts.
Yes, they are different lifts.
Okay.
So this as you can... You can choose it to be a constant map. And basically what you get is a connection. So this, on this bundle, there is a standard connections. Say, for example, if your sigma is equal to sigma L1, then you will get a connection which looks like this. So A1, B1, so this is L. AL, BL, so those are the generators for the Riemann surface, and you have one for the RP2. And then here is something called epsilon. So this epsilon is the constant value you choose here. So you just choose Sx, say if it's epsilon, this element, then this epsilon square equals to 1. And of course, you know that if it's written in this form, you know the topological type by looking at the obstruction. Yes. Yeah, so what I'm saying is that I don't mean to say all the S give you the same portion downstairs. I didn't mean that. I just say that you would have different, but then there are some which look like different S, but then they will get the same. And then eventually you will have different S. And so for this inclusion, the image of that is precisely the fixed point set. Okay? And then you see that, so this space is totally real, totally geodesic, Lagrangian submanifold because of this anti-holomorphic thing. And also because of this, we can define, sorry, this is 3. We can also define the Yang-Mills functional on the space of connection over the non-orientable surface. So we define the Yang-Mills functional on the space of connections downstairs by taking the Yang-Mills functional upstairs, so it's P tilde, and you restrict it on the fixed point set. On the fixed point set. And the critical point of this Young-Mills functional are called, again, the Young-Mills connection. And so you see that this NP are those Young-Mills connections downstairs are precisely those Young-Mills connections upstairs, which are invariant under this tau tilde star. And so you can get, so if AP is a stratification upstairs, then we can get a stratification downstairs by taking the intersections. AP is, so for now I will just write this. So this is very natural, you just get a stratification this way. But the thing is that this intersection could be empty. So you really need to know what the Young-Mills connection looks like and how the evolution works. So with this, we have a general idea of the stratification is, and so there are two parts that I need to talk about in the remaining time. The first is we need to see what is the Morse stratification, or what exactly does Young-Mills connections look like. Those critical points. And then after this is clear, we can do the Morse inequality, which means that you can try to see how the strata fit together. Okay. So first, I'll just say Young-Mills connection. So sigma now is L0, L1, L2. We can deal with this all together. So it's orientable and non-orientable, and we can define a map called the degree. So degree is a map going from the fundamental group of the surface into Z mod 2Z. And so what it does is, so you have an element in this fundamental class, it's a loop. And so you send it to the first Stefan-Winnie class of the pullback of the tangent bundle under this. So you will have 0 or 1, depending on orientable or non-orientable. So that you will get 0 and 1. And so with this degree, you can define the supercentral extension of the fundamental group. I will write it here. So you have this exact sequence. So if you have any R, you send it to something called JR, and then A sends to beta A. And so there are some relations here. So first of all, this R thing. So JR1 plus R2 is JR1, JR2 in here. And then the relations between this JR and A is the following. So A, JR, A inverse. So I'm not specifying any loops here. I'm just saying any elements. So A, JR, A inverse is equals to JR if the degree of beta A is 0. And it's JR, J minus R, or JR inverse if the degree is equals to 1. So what this degree means basically is that, so in the fundamental group, if it's orientable, then those just orientable loop, then the degree of those loops goes to 0. But say if you have a non-orientable surface, you will have an RP2 part. So the generator is, say, C, then this degree of that C gives you 1. And then lastly, there are some relations coming from pi 1 sigma and this R. So I will write out precisely how the generator and relations are in the next blackboard. Okay, so you have this. So this is the central extension. And so you see that. So if all the degree is 0, which means that your surface is orientable, then the relation is AJR A inverse equals to JR. So that's the usual central extension that we are familiar with. So the remark is that this is the central extension of the fundamental group that we are familiar with if and only if sigma is orientable. So using this central extension, we can now write out precisely those Yang-Mills connections up to gauge transformation. So this is a theorem. So orientable with down by RTL but and we did the non-orientable part. So the moduli space of Yang-Mills connections over sigma Li with respect to this group, the structure group G, is you consider all the possible principal bundle over your base space, and you take the space of Yang-Mills connections mapped out by gauge transformation, then they are precisely this supercentral extension mapped out by G. And if you only map out by the base gauge group, then they are the home of this gamma R. And so the G act here, I will write out, so the G acts by conjugation and adjoint action. So I will write out precisely what this is. And you will see those actions. So this home if it's orientable, then you would have 2L generator and an element coming from the Lie algebra. So this means the Lie algebra. And you have a relation which is the product of the commutator equals to exponential x, and because those things has to commute, so you have AI, BI lies inside of the stabilizer of x for all I. And for non-orientable surface, so again you have 2L generators plus 1 which come from the RP2. Oh, I'm sorry. And then with the relation, that is the product equals to exponential x c squared. So those are from the fundamental group relation. And again, your AI, BI are in the stabilizer of x because those commute thing degree is 0. But for C, it's not commutative, so you have a joint Cx equals to minus x. And for the Klein bottle, you have 2 generators for that Klein bottle thing. Inside of g to the 2L plus 2, and in the Lie algebra, and the relation, of course, is the product of the commutator equals to exponential x, and Klein bottle is C, D, C inverse D. And AI, BI, and also D, they are in the stabilizer, and only C doesn't commute with it. So you see there are group element and there are the algebra element. So this part is the conjugation action, and this is the adjoint action. All right, so the stratification so now we are at so on the spatial connections for either orientable and non-orientable can be directly see from this home thing. So the moduli space. So let sigma L is 0. Then what you see is this moduli space. this I will just give you one example, the unitary group, so that you will see how you get the strata directly from looking at the supercentral extension. I will introduce a notation X. Just means that the representation varieties consider the Yang-Mills connections with respect to UN group. So now your G is UN. And the relation UN. So on this moduli space, you can pick one unique representative. You pick one unique representative by asking this X to lies in the fundamental wire chamber. Okay, and together with the relations that the product equals to the exponential x, our x turns out must be in this particular form. So you have k1 divided by n1, and you repeat it n1 times. It's a diagonal matrix, so everything else is 0, and then k2, n2, k2, n2. Repeat it n2 times, and then kr, nr, kr, nr. Such that those kj's are integer, nj are positive integer, and summation of nj is n, and they are decreasing. So we can define an index set using this information, and that is all our strata. And this actually recovers Atiyah-Bhatt's work, which they call the strata the Atiyah-Bhatt type, but they get that from using the Harder-Narashan filtration. So you see they are precisely like that. So we can define this index set. Let I, N, K be mu1, mu_n, such that repeated n1 times kr, nr, repeated nr times summation kj is equal to k, nj is equal to m, and they are strictly decreasing. So this is the index set, and because ORX looks like this, we know that this moduli space can be written in terms of this. So the moduli space of Yang-Mills connections for UN are precisely all this. So k is any integer, and mu lies inside of this index set. And you have A1, B1, BL, X, C mu such that, I'm sorry. So this x mu, so C mu is the conjugacy class of x mu. So for any mu, your x mu looks like that. So this gives you all the stratification. And so this K represents all the topological type. So when on your UN bundle, you have Z, different kind of topological type. So this K tells you what the topological type you are looking at. And this I and K, when you fix a K, it gives you all the strata. So this gives you all the strata. Okay, so I would say that for sigma, sorry, I haven't even said the reduction formula. So for each strata looking like this, you see that this is a conjugacy class. So after this UN, you can make this whole thing disappear. So you will have x mu. And because your x mu looks like this, so basically they are breaking into all the block. And so your x L0, ym, un, for this mu, actually it becomes the product of other Yang-Mills connections of this smaller group, because those are U and J, and modeled by this action, U and J, and the strata you consider is the central one, so the minima one. So Kj and J, Kj and J. So this is the strata you consider. So any strata will be reduced to the product of this other strata, which are the minima strata of smaller rank. So this is the reduction formula. So for each strata, you can reduce it. So this is the reduction formula. So this reduction formula is important because when you do the Morse theory, you do need all the information coming from all the strata. So this tells you a way to relate those things. Okay. All right. So for sigma L1, sigma L2, I would just say a quick word. So this tau. So also you do this whole thing is coming from this supercentral extension, and you can see how those type X need to look like. And actually that corresponds to this tau tilde star induces a tau 0 on the index set. So we know that for any topological type downstairs, the pullback is always topologically trivial. So in the UN case, so this G is also UN, the degree is 0. So that's the index set, IN 0. And this is the tau. This tau actually looks like this. So this evolution actually maps this strata to this strata. So the strata which actually have intersection with the fixed point set are those strata which are invariant under this tau 0. So they will be like this, K1, N1, and repeated N1 times, and then you have KR, NR, repeated NR times, and you might have 0. It's okay. And then you have minus KR, NR, all the way to minus K1, N1. So that's the type. And that also tells you how the reduction formula should look like, because this part corresponds to the flat one. So this descends to the flat connection over the nonorientable surface. And these two parts combined will give you something in the double cover. So that will give you a representation varieties on the double cover. So when you do the reduction, you not only need information coming from a smaller rank over the nonorientable surface, but you also need information coming from the double cover. So I would just leave it like that. I'll have 3 minutes. Let's see how that's going to work. So the second part is the Morse inequality. So we want to see how the strata fit together. So that we fix a total ordering on the index set. So now we consider just whatever simplification we have, and let ij be to index set. So this is the index set of the strata. So I is any strata that is smaller than lambda. J is I union lambda. Okay? So with this 2 index set, you can consider the long exact sequence of this pair. Okay? So we have AJ and we have a long exact sequence. So this n lambda is the normal bundle over a mu a lambda naught is the complement, so minus the 0 section. And you would have a long exact sequence for this 2 pair, AJ, AI, and n lambda naught. So this is the one for HAI. So G is the gauge group. And you have one for n lambda. And from here to here is an isomorphism because the excision. From here to here, you can look at the time isomorphism minus d lambda a lambda. So d lambda is the codimension of a lambda. And so here, by the inclusion, and here, isomorphisms, a lambda. So here is by cup with the Euler class of the normal bundle. Okay, so I don't have any time. So what this Morse inequality to do is that this part is the time isomorphism. So first of all, you need to prove that for the nonorientable case, this is this normal bundle is orientable. Otherwise, you only have time isomorphism up to the Z2 coefficient. So you need to prove the orientability of that. And then secondly is this is the strata coming from AI. So this is just you going one step further. And then so what you need to know is you need to know the kernel. So that will give you the information on how the strata fit together. Yeah, so I will not talk about that, I guess. Okay, thank you very much.
Interesting.
So by pulling back, you get a map from the Moduli space of flat connections on the non-orientable surface to the Moduli space of flat connections on the double cover. So what do you know about this map? I mean, does it have, the image has several connected components?
Right, yes.
Do you know the dimensions of them?
Yes.
So
the moduli space, so if you look at the moduli space of flat connection on the double cover, then of course there is itself has an involution, and the fixed point set of that involution, you have a map coming from downstairs. So the moduli space downstairs going up. And in some cases, so there is a precise formula for that. So you will know precisely in what situations this map is a one-to-one map. In some situation, it's a covering map, but you always have something goes inside of it. And they are very precisely, you can use this home thing, you can write it out.
And are there Lagrangian components?
Yes, yes, yes.
But all of them are Lagrangian?
Yes.
All of them are Lagrangian?
Yes, because it's just the connected component of this whole thing. Yes.
And you actually interpret upstairs on the orientable surface in terms of identifying your variety, your representation variety,
Yes.
in terms of holomorphic bundles.
Holomorphic bundle.
Yeah.
Right,
on
yes.
the cover.
Yes.
In terms
So
of the Moduli space of stable bundles.
right. So we have a map. So upstairs you write the strata, and in those strata there is a one corresponding to the holomorphic structure. And then so this tau, you would actually have a tau on the holomorphic structure. And then that's how you, so if you say this tau now is on the holomorphic structure, then it goes from the holomorphic vector bundle into this tau pullback. And this is the complex dual, that's the complex conjugate. And or if you say the holomorphic structure, then what it does is, so of course this combined with the Hermitian metric, you will get a Hermitian connection. And then you take the 1-0 part, and then you use this tau to pull it back. That's also, yes. So that's the evolution which corresponds to this tau. Of course, there are different kind of evolutions on the holomorphic structure, but this is the tau that comes from the deck transformation.
Other evolutions that give you the same deck transformation.
Right, but you want to have a bundle which fits with that bundle you start with over the non-orientable surface.
Here, but we determine the topology of these spaces.
Yes.
We begin by determining the topology of the gauge group.
Yes.
And what does it here?
Right. So we also compute that because we need to.
Is it?
We have an explicit formula for the equivariant Poincare series for that total space, which means the classifying space of the gauge group. Yes, we have the Poincare polynomial for that.
It's complicated to say what it is. I mean, here, but it's very simple.
Yes, it's not. I can write it out. So say for example, if for u, of course we look at the rational coefficient.
Yeah.
Yes. For un, so the pt, bg, p is just the product 1 plus t to the 2k minus 1 to the power of 2l plus I minus 1 divided by 1 minus t2k. So that's the, yes. Yes. So we also have a way to compute this Poincare polynomial, but it's not perfect, not like in the Untitled case. It's the other extreme case. That's what I said in the abstract, the anti-perfect. Yeah.
At the end of the day, you compute the Poincare polynomials of some
the
of these moduli spaces.
Yes, for the flat connections when your group is U2, U3, SU2, SU3.
Well, we resume at 11:30 for the next talk, and let's thank.
Thank you.